In this video, I will talk to you about logistic regression. So if the dependent variable is discrete, either 0 or 1, for example, the stock price may go up or go down, then this is a logistic regression problem, or basically it is a classification problem. The hypothesis is a function of z, and z is actually theta transpose times x. The function is a sigmoid or logistic function, and it is equal to 1 divided by 1 plus e to the z, to the negative z, sorry. So with z equal to theta transpose times x, then this is the hypothesis. And this figure shows you the sigmoid function, and there are asymptotes at 1 and 0, and right here we have 0.5. It is where z equal to 0. The sigmoid function is between 0 and 1, so can be interpreted as the probability of y equal to 1 given x and the parameter theta. So if z, which is equal to theta transpose times x, is greater than or equal to 0, then the sigmoid function is greater than or equal to 0.5, then we predict that y is 1, and otherwise we predict that y is equal to 0. So in the figure at 0, the sigmoid function is 0.5 with other values of z which is greater than 0. Then we have other values of the sigmoid function which are greater than 0.5, and here we predict that y equal to 1, and the probability of y equal to 1 and the probability of y equal to 0, the sum of them is equal to 1. Now let's talk about decision boundary. For example, we are given a data set with a number of instances, and for simplicity we consider a two-dimensional problem with two features, x1 and x2, and let's say this is x2 and that is x1, and assume that from the data we get the vector theta, the parameter that makes the cost function minimal. So the decision boundary is where z, this is z greater than 0, greater than or equal to 0, and z is actually equal to theta transpose times x. So we plug them in, right? This is theta, and x is a column vector containing 1, x1 and x2. So we get this, and then switch negative 28 to the other side, we get that. So from there we draw the decision boundary, and actually this is x1 and that is x2, and on one of the side we predict y equal to 1, and the other side y equal to 0. Now let's look at another example. Now I have another data set, and looks like that the decision boundary is nonlinear. This is also a two-dimensional problem with x1 and x2. So let's say this is x1 and that is x2, and here we add the quadratic terms. Similarly, assume that from the data we get the vector theta that make the cost function minimal. So from there we can draw the decision boundary. So it is where z is equal to or greater than 0, and z is actually equal to theta transpose times x. This is theta, so we plug it in, and x here would be 1 x1 x2 x1 square and x2 square, and the result is this and that, and from there we can draw the decision boundary, which is actually a circle. Now we look at the cost function. This is cost function in linear regression. So if we use this function, then this may be a non-convex function and may have multiple local minimums and may not find the global minimum. So we need to define another cost function. So let's define a new cost function, and the new cost function also have 1 divided by m times the sum from with I from 1 to m, and inside the sum we have the individual cost for the ith instance. Now we look at the case when yi equals to 0. So look at this case first. We can see that this part is gone. So finally the individual cost for the ith instance is just that, and 1 minus yi is equal to 1, right? So what we have left is just this. Now if h of x at xi, so if h of x at xi is equal to 0, then the individual cost is equal to 0. So it captures the intuitions that there is no cost when h of x at xi is actually equal to the actual value of the independent variable. And if h of x at xi is equal to 1, then the individual cost is infinity. So it means that the cost is very high, extremely high for wrong classification. And on the other side, if yi is equal to 1, then the individual cost is just that, because this part is gone, and yi is equal to 1, right? So what you have left is just this. And we also look at the case that h of x at xi equal to 0, and the individual cost is equal to infinity, and the cost is very high for wrong classification. And when it is equal to 1, then the cost is equal to 0, meaning that there's no cost when h of x at xi is equal to the dependent variable, the actual value of the dependent variable. A nice property of this cost function is this. The cost function is convex, so we can always find the global minimum. If we take the derivative of the cost function with respect to the parameter theta j, after several steps we can get to this, and this is actually the same as the derivative in linear regression. So from there we get to the gradient descent for logistic regression. Just by looking at this, you can see the algorithm is very much the same as in the case of linear regression. Only the difference is the hypothesis is different, because here we have the logistic or sigmoid function. So basically, logistic regression is a classification problem with two classes, 0 and 1. How about the case with more than two classes? Then we can use the 1 vs all strategy. In the training step, for each class k with k from 1 up to capital K, we train a classifier hk of x, which classifies class k and non-k. So basically still two classes, right? Class k and non-class k. So for k class we have k classifiers, and then in the classification step, given a test instance, assign it to the class that maximize hk of x, and this is actually k.